Hi there. Thanks for joining us once again. This is a Q&A edition of Space Nuts. My name is Andrew Dunkley. Great to have your company. We will be answering audience questions exclusively on this episode. We'll never do it again. Yes, we will. We're going to be looking at a concept that Ross has put up about black holes equaling dark matter. We'll explain that, or he will, and we'll try and tear it apart. Sandy is asking about navigation in space. John is talking relativity, time, black holes, and the big crunch. I knew we'd get a question about the big crunch because we talked about it so recently. And the speed of re-entry is a question from Andy. We'll deal with all of that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And with us once again is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. Good to talk again. It seems like only a few minutes ago that we were talking.
It does,
before.
doesn't it?
Yes, extraordinary.
That's called relativity, I think. Yeah.
Time dilation. Yeah.
I'll tell you something funny. We had our granddaughters around last night. They were supposed to stay the night, but they both chickened out, so Dad had to come and pick them up at 9 o'clock. But they were having a bit of fun, and they liked doing craft. And one of them built a telescope with a piece of paper and was looking through it. And Judy said, "What have you made?" And it was the 4-year-old. She said, "I made a looking through thing." That's what a telescope is. It's a looking through thing.
Which is nearly what they were originally called before the
Is that right?
telescope was intended. Yeah.
She's way ahead of her time.
Device
way
for
behind.
device for seeing afar.
Yeah, well, a looking through thing.
Looking
is what she
through
called
thing,
it.
yeah.
Very cute.
I love that. Yeah.
Yeah, it was good.
Yeah, you don't know what you might have, released in that child's brain. She might
No.
become the next great astronomer using a looking through thing to make discoveries about the universe.
Yeah. Well, that's why we called her Vera. No, her name's Felicity.
That's a good name as well. I like
Yeah.
Felicity.
It is nice.
Yeah.
Shall we get to our first question?
Oh, all right.
All right. If black holes are the center of most galaxies and have been eating up matter almost from the beginning of the universe, can this be a possible explanation of dark matter? The black holes have eaten it. Now, this comes from Ross Simon. I had to smile when I read his name because Ross Simon used to be a famous newsreader on the Australian Broadcasting Corporation's TV news service. I remember Ross. He was brilliant. Might be the same one. You never know.
I was going to say, it's not the same Ross, is it?
I hope so. It would be lovely, but it
would
doesn't
be
matter
lovely,
if it's
yeah.
not.
Yeah. So whether or not you are the famous Ross Simon, Ross, lovely to hear from you. And I mean, it is tempting to lump black holes and dark matter together. And indeed, that was looked at as being one of the first explanations of dark matter, that we've got space full of black holes that we don't see because they're black holes, and that they might account for the dark matter. This was the so-called macho theory, massive compact halo objects, which was popular in the 80s, because it was only in the late 70s that people started taking the idea of dark matter seriously, when we realized that something like 80% of the matter in the universe is invisible to us. Now, that's perhaps slightly different from what Ross is asking about, because he's talking about material being sucked into black holes, and that is certainly something that happens, but that's not matter that's missing. That's just gone. The bottom line is that the universe, as we see it today, has this mystery in that we know that there is stuff there that has a gravitational effect. It holds galaxies together. It holds galaxy clusters together, causes gravitational lensing all over the place. But we have no way of detecting what it is other than through its gravity. So it's some people used to call it missing matter. It's not missing, it's definitely there. This dark matter is around, and it's probably in the rooms that you and I are sitting in at the moment, because it tends to be where normal matter is. And we think
Judy and I were actually talking about a dark matter the other day, but I won't elaborate.
Well, what you do in your spare time, Andrew, is entirely up to you, especially with your wife. But the black hole thing did come in because of this theory back in the 80s that MACHOs, massive compact halo objects that are kind of dead stars or orphan planets, or more especially black holes, might be the source of dark matter, the source of this gravitation that we see present on large scales, like galaxy clusters and galaxies. What ruled that out was work carried out at a number of observatories, including here in Australia. In fact, in a survey which was called MACHO, looking for these things, and it was that if you had a universe full of black holes that you can't see, you would still be able to detect them by what's called gravitational microlensing, because occasionally one of these black holes would pass in front of a distant star, and because black holes distort the space around them, that behaves like a lens, and you magnify the light of the distant star. So you get a microlensing event has a very characteristic shape. It's a star getting brighter to a sharp cusp and then fading away again, quite symmetrically. And we do see them. They're caused by normal stars and their planets. But in the numbers that you would have to have for black holes to be dark matter, they are not there. There weren't enough. The numbers were far too low. And that's when the emphasis shifted to WIMPs, the weakly interacting massive particles, which is just one class of subatomic particles that we think dark matter might be. So that's where the theory stands at the moment. So black holes, and I think Ross is talking about supermassive black holes at the centers of galaxies. Yes, they've been swallowing stuff up for 13.8 billion years, as far as we can tell. But they don't explain why in today's universe, something like 4/5 of the matter in the universe is invisible to us.
Yeah. Well, there's so many things we don't understand. And as yet, which was brought up in a question recently, we have not been able to capture or identify a dark matter particle. So, until we can find some absolute proof and study it, we're probably going to just keep working with theory, I would imagine.
Yeah, there are techniques that can be brought to bear. One of the theories about dark matter is that while dark matter particles don't interact with normal matter particles, they may interact with each other. In other words, if you bring two dark matter particles together, it's thought they might annihilate and produce a signal in gamma radiation. So you get this flash of gamma rays, which might have a characteristic spectrum. And people are looking for that phenomenon in the centers of galaxies, because that's where you would expect the dark matter to be at its densest. So it's where you would expect the dark matter particles to interact with each other. So far, the results have been a bit mixed on that, but it's one possible way that we might eventually discover what dark matter is.
Maybe dark matter is like a negative photograph. Remember, in the days of manual photography, you'd take the film and it would be negative, and then you turn it into the photograph. Maybe dark matter is the negative of the universe.
Well, I mean, there might well be a way that there is a sort of dark, what can I call it, a dark particle physics, a whole sweep of subatomic particles which fall under what we lump together as dark matter, but it's not just a single particle, it's many different ones, just like the particles of normal matter, the 16 normal matter 16 subatomic particles. They include forces as well as matter when you count the 16. But you know what I mean. You've got this suite of different particles that make up normal matter. Maybe there's a suite of different particles that in some ways are a negative that make up dark matter. So I think that's
a
not
thought.
a bad way of looking at it.
We've been assuming it's just the one thing. It could be all sorts of things.
It could be. There could be. There could be atoms and molecules made out of dark matter because they interact with each other. I don't know. Look, I'm not a particle physicist, but the possibilities seem not exactly endless because particle physics has certain rules that you've got to follow. But I'm still pretty optimistic that we're going to get to the bottom of dark matter, hopefully while I'm still alive, because I want to know.
Yeah, we all do. We all do.
Yeah.
Thanks for the question, Ross. Really good discussion point. We get a lot of questions about dark matter and black holes. While we're on the subject of black holes, there was an article released on the BBC early this year. I know it's still early this year, but I'm talking the 3rd of January, where scientists captured the first ever visual proof of 2 supermassive black holes in a death spiral. So we're really starting to be able to find out more and more through our increased technology and the capacity to observe and create images of these things. So that was a pretty exciting story. I read that one the other day. I thought I'd give it a mention, but they of course, the popular press created their own photo, which has absolutely got nothing to do with it. But it sells the story, doesn't it? But they've got the image of these 2 black holes, basically getting ready to devour each other. I think the big one will win.
Yes,
probably.
Well,
thanks, Ross.
Yeah, probably.
Yeah, thanks, Ross. Good to hear from you.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Our next question comes from Sandy.
G'day, Fred and Andrew. It's Sandy here from Melbourne again. Thanks for a cracking show as usual. My question today is about navigation in the solar system for the various spacecraft that we've sent into deep space. Being a sci-fi nerd, my mind naturally goes to fancy graphics of star charts and orbit parts on a giant screen. However, I wanted to ask how mission planners at various space agencies plot orbits. Do they take into account objects like asteroids for any close calls, or is the space so vast it's not really necessary? Thanks heaps, Sandy. Cheers.
Thank you, Sandy. Good to hear from you. I don't think we've heard from Sandy in a little while, but he does a lot of great astrophotography, and he's got a pretty amazing setup that he's shown me in the past about how he does it. Computers all plugged into telescopes and all this great software. It's a bit out of my league, but I might get there one day. Navigation in space, plotting orbits, all that kind of jazz. I must confess I struggle to get my head around it. Like it's not like driving a car. You've got to do, when it comes to space, you've got much less resistance, much more reaction to minute thrust and micro thrust and all sorts of other things. But you've got to be looking in all directions, not just, on the plane of the planet when you're driving a car type of thing. I don't know what I'm trying to say, but how does it all work, Fred?
It's sort of the equivalent of plotting things on a screen, but not quite the same. But yeah, the idea that excuse me a minute. That's I'm sorry, I've got this cough. Sandy's idea that we need to take into account. I'm all right. We need to take into account the positions of asteroids and things of that sort. That's exactly right. So when you chart the pathway through space, which is all done numerically, it doesn't. We can make displays of them, and I think people do as well. But the reality is that the real hardcore is locked up in the numbers and the equations. What you have to do is to, at any instant along the orbit of the spacecraft, because it is always an orbit, usually For something like, going between the planets, it will be in orbit around the sun. That's the way orbital mechanics work. As soon as you switch on your thrusters, then you change that orbit. But when all the thrusters are off and your main engines are off, you are following a trajectory, which is essentially an orbit. Not always a closed one. It could be an open orbit, which is what's happening to the 5 spacecraft that are leaving the solar system. So, but that orbit, it's the future position of your spacecraft is dictated by the gravitational influence, not just of the sun and the Earth and probably the moon, but all the planets. All of them exert a gravitational pull, and that goes down to the asteroids as well. If you're passing through the asteroid belt, you need to know where they all are. They would all the ones which are known, and there's more than 1 million known asteroids now. You would have them kind of built into your software that's looking at the direction that your spacecraft is going in. If there was any risk of a collision, it would flag that, and it would also take into account the gravitational influence of any close encounters of asteroids. So it's a very precise science, as you know, because we know when, for example, the New Horizons flyby of Pluto a decade ago, in 2015, the precision with which that was executed was unbelievable. And it's because of orbital mechanics and how well we understand these gravitational influences that let you do that. Yes, space navigation, in some ways it's easier than navigation than driving a car, because with driving a car, you've always got to the unpredictability of the other road users. The great thing about orbital mechanics is you know what the other planets, the other asteroids, and all the rest of it are going to do. And just one other adjunct to this, if I may. Some years ago, there was several papers which talked about the interplanetary superhighway. And these are effectively low-energy trajectories between the planets. And it's based on exactly what I've just been saying. You can map where the gravitational pull of all the objects will take you. And it turned out that if you can put a spacecraft at one of your Lagrange points, these gravitationally stable points, then leading from that are these various low-energy pathways that take you to the Lagrange points of other planets. And that's the interplanetary superhighway. It might take you decades to get from the Earth Lagrange points to something like Mars's or Jupiter's Lagrange points. It's a very slow process, but it does exist. This almost like an imaginary highway, which is changing all the time as the planets go around in their orbits. Just an interesting aspect of the navigation in space.
Yeah, I would imagine that a lot of this would be pre-programmed into the computers of these vessels. They do everything ahead of time, because these things are on autopilot. The long haul spacecraft that are going out to do these missions. So it would, and I've been in the cockpit of a commercial airliner long before you can't do that anymore. Long before we had any issues like that. But and watching the process, like the plane flies itself, and the pilots sit back and tell dad jokes to the tower. No, that's what happened. But I would imagine it's the same in space. All these things are pre-programmed, pre-calculated, and then contingencies built in just in case something gets in the way that you didn't anticipate. They'd modify the spacecraft to sense a problem and go around it, I would imagine.
Yeah, and in fact, the likelihood of something, it's so predictable, and our knowledge of the sort of congestion in space, if I can put it that way, is so deep that it's unlikely that something's going to come along to surprise you. You suddenly see something ahead that you've got to avoid, because that avoidance might actually be very difficult. You can do things. So perhaps the best example I can give you, again, it goes back to New Horizons, and that is that once the Pluto encounter had happened back in July 2015, they looked for other potential targets. and
That's right.
eventually found the object Arakoth that was discovered as part of surveys looking for future targets. And they worked out at what point they had to apply a thrust to the spacecraft to change its trajectory so that it would intersect with Arakoth. And it all happened, perfectly smoothly. I think it was a couple of years later when the Arakoth flyby took place. I can't remember when it was, maybe even a bit later than that, maybe 5 years later. but that all happened. That was the nearest thing to, there's something ahead, we need to change course to either interact with it or avoid it. And it was a very leisurely process.
And you're right about navigation on the planet on roads being much more dangerous. We were walking along the street the other day, and somebody turned right off the main road into our part of town and went to the right-hand side of the traffic island instead of the left, right where we were walking. So, yeah, I don't think she noticed, to be honest. She just went up the wrong side of the road. Anyway, it happens. But we always keep an eye out for that kind of thing. There you go, Sandy. Thanks for the question. The answer is easy peasy, really.
With modern computers. It's a lot harder if you're doing it by hand.
Yes. All right. This is a Q&A edition of Space Nuts with Andrew Dunkley and Professor Fred Watson.
Space Nuts.
Okay, our next question comes from John in 27 parts. Hey guys, love the show. Every time I listen to a new episode, my mind goes crazy thinking about new possibilities and questions. I have two questions about time dilation. In general relativity, if general relativity causes time to be observed at different rates, would that mean someone orbiting very close to one of the first black holes in existence would experience a universe that has existed for a much shorter period of time? As a follow-up to this, if the new theory about the Big Crunch turns out to be true, would the finite time of the universe form the Big Bang from the Big Bang to the Big Crunch be considerably shorter if, again, you were orbiting close to a black hole? We see the universe as being 13.79 billion years old, and new estimates put the Big Crunch at 20 billion years into the future. My brain hurts thinking that these timescales could be considerably different due to time dilation. All the best, John from Suffolk in the UK. Ooh, there's a lot in there.
And so it's quite complicated because time dilation depends on your vantage point. So, if you're in orbit around a black hole, you're in an intense gravitational field.
You're also stuffed, but we'll just
deal with
that another time.
You experience time just at the normal rate.
Yeah.
What an outside observer looking at you would see would be your time going very slowly. The time would be dilated. So I suppose what we're talking about here is that in terms of what you might call the frame of rest of the universe itself, that's what we see when we look at the universe in general, and that's what gives us the 13.79 or 13.8 billion year age of the universe. Your perception of that, so that time effectively wouldn't change, but your perception of it, if you were in orbit around the black hole, it would probably appear to look as though it was going very quickly. But that's because your time's slower. And likewise, with the density of the universe being higher at earlier stages. Yes, we do know time dilation takes place. You can actually see that because when scientists look at the light curves of supernovae, exploding stars, they have a light curve, their light increases and then decreases in a more gradual way with a very characteristic shape. Those light curves are dilated, they're stretched when we look at ones in the early universe. So the phenomenon does happen, but it doesn't happen at a level that's going to significantly shorten our perception, the universe's perception of its own history, if I can put it that way. I think I'm talking a little bit in riddles here, but I hope John follows me that it really is all about your frame of rest, as we call it, your vantage point on the universe, because that's what time dilation is all about. It's about people seeing time going differently depending on their viewpoint. Our viewpoint here from Earth is probably that of the universe as a whole, effectively, because we are not in an intense gravitational field. The gravitational field of the sun is the strongest thing we feel that keeps the Earth in orbit, but it's nothing like what you would find around a black hole. And so we've got probably a fairly unbiased view of the universe and its history.
Are we in a gravity well?
Yeah, we are. I mean, the Earth itself creates a gravity well, and that's what keeps us stuck to the Earth, because the gravitational potential at your head is a little bit different from what it is at your feet, and that's what's pulling you down, the changing shape of space.
There you go. All right.
But not spaghettifying you.
No. So did we unpack everything there?
Yeah, I think so. I think we covered most of it.
Okay.
I know. Sorry, go ahead.
No, I was going to say that he also asked if the big crunch would happen faster than the expansion.
So that I kind of lumped that into the fact that the times that we observe from our location in the universe, probably 20 billion years down the track seems about right for the big crunch. If the recent DESI results, it's what happens. I was going to say that, like you, John, these things make my brain hurt. So don't think that it's peculiar to a few people. I think most physicists, they really have to get their heads around the things like seeing things from different vantage points. It's not it's not intuitive at all.
No. All right, John, thank you, and I hope all is well in Suffolk. That's basically what one of the easternmost points of England, isn't it?
I used to live in Suffolk.
Oh, there you are.
Not far from Cambridge, which is in Cambridgeshire, but Suffolk, I was over the border in Suffolk. You're right, Suffolk, Norfolk and Suffolk are the two counties in East Anglia, that sort of semicircular bit that sticks out not very much north of the Thames estuary.
There you go. All right.
Very pretty
Thanks,
part
John.
of the country. Yeah.
Yes. Good to hear from you. Our final question today comes from Andy.
Hi, guys. This is Andy from London. I'm a new listener to your podcast and quite new to science. So forgive me if this is a stupid question. But I was just wondering, when craft re-enter atmosphere and they have to come in at a certain angle to stop from burning up, why do they not just come through slowly to get away with the friction effect, which causes the heat? Thanks.
Thank you, Andy, and thanks for finding Space Nuts and being a new listener. You've only got 590 odd episodes to catch up now, so have fun with that. We've certainly had fun with it. I think we've had this question before, maybe asked a different way, and when it comes to a spacecraft, we're orbiting the planet, which is essentially, it's just constantly falling. You're just maintaining a velocity that stops you falling in. You do have to slow down to re-enter so that arc is reduced or increased. Can't remember which. And then you fall through the atmosphere. You can't stop and just sort of ease your way back in, as against a space elevator, which would be able to do that if we ever build one. But that's a different set of... But a space elevator is essentially not orbiting. It is stationary to a point on the planet, which means it goes up and down. Is that making sense?
Yeah. Yes, it is.
Well, that's good. That's the first time ever.
Everything you've said is correct. Space elevators are hypothesized Buzz Aldrin told me that night I had dinner with him, it's never going to happen. And he was quite right, because the space elevator has to sit on the equator. Every spacecraft in the sky crosses the equator, so you're always going to get things banging into it. It will be very difficult to build one, apart from the structural thing. So neglecting the space elevator for a minute, what you said is absolutely right. In order to stay in orbit, you have to achieve basically a horizontal velocity of about 8 kilometers per second. And that's, otherwise you just fall back to Earth. So that's what all the huge amount of fuel that is carried by a rocket being launched, that's what it's all about. It's about getting up to a height of 200 or 300 kilometers and getting that orbital velocity, getting that horizontal velocity of 8 kilometers per second. So what you could do is, and going, this is hopefully helping Andy, if you had unlimited amounts of fuel, you could turn the rocket round from its orbital position and fire your rockets to act as a braking system to slow the thing down. And then you could gently tiptoe down through the atmosphere, constantly firing your rockets. It's actually what Musk does with his Falcon rockets. He's got enough fuel left that he can bring the empty spacecraft back down intact and use it again without needing a heat shield. So you could do that, and he's demonstrated that we can. But it turns out that it's much more effective to use this process called aerobraking, where you actually use the atmosphere itself to slow the spacecraft down, because you don't need any fuel for that. You just need something that's going to stop it burning up. So getting from this 8 kilometers per second down to a few, a meter or two per second for a splashdown or a touchdown is the tricky bit. And you've got to, you've got to use whatever means that are at your disposal, and the easiest one is aerobraking, using the atmosphere itself to slow you down. I should point out that I think the first stage Falcon rockets, they're not at orbital velocity when they turn around and come back. They haven't got up to that 8 kilometers per second, because there's a second stage that lets them do that, and they still burn up, basically coming back into the atmosphere, the second stages. Good question, not a stupid question at all.
No, and it's rocket science. I mean, we often say when something's not difficult, it's not rocket science. This is rocket science. Orbital speeds are significant. They're to stay out there, they've got to do 17,000 miles an hour.
Which is 8 kilometers per second.
Yeah. Mach 25. To slow down so that you can return to Earth safely, you've got to go from that speed to subsonic speed.
Yeah.
And using fuel to do that would be exhaustive.
Yeah, that's right. That's exactly right. Basically, you're looking at the same amount of hardware in terms of a rocket and its fuel to get you up there. You'd need the same amount to bring you back, just to do a gentle touchdown on the Earth. Notwithstanding the first stage recovery that we're starting to see with, well, not starting, they've been doing it for 10 years with the Falcon 9 rockets.
I'm sure the technology will improve and we'll find better ways. But at the moment, using the atmosphere as a free braking system works really well.
It does.
Except when it doesn't, but that's only happened a couple of times.
Yeah.
Thank you, Andy. Great question, though. Really appreciate it. And don't forget, if you've got questions for us, you can send them through via our website, spacenutspodcast.com, spacenuts.io. You click on the little AMA link at the top, which means Ask Me Anything. I finally figured that out. Ask Me Anything, AMA. And you just fill in the blanks, whether it's a text question or you can hit the start recording button and record a question for us. Any device with a microphone will do. spacenutspodcast.com or spacenuts.io. While you're there, you might want to hit the supporter button and look at ways of supporting us financially. It is not essential. We do not demand that of you, never will. but we do have a lot of people who volunteer to do that. In fact, it was the listener's idea in the first place to set that up for us. We didn't even think about it until someone said, how do I contribute to the program? And it all took off from there. And we do appreciate our supporters very, very much. Thank you so much for thinking enough of us to put a couple of bucks behind our words. We appreciate it greatly. I think we're all done. Fred, thank you so much.
A pleasure, Andrew. Great to hear from the listeners, as always. Great questions. Get my mind thinking again. So thank you, everybody. And thanks to you, Andrew, too, for keeping it all on the rails.
I do my best, and sometimes I don't. But yes, thank you, Fred. We'll see you next time. Professor Fred Watson, astronomer at large. And thanks to Hugh in the studio, who definitely does keep it all together, although he couldn't be with us today because he re-entered his garage at excess velocity, couldn't get down to subsonic speed, and, well, he'll be in traction for a couple of weeks. From me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.